Hi, in this video we'll discuss about energy for simple harmonic motion. Let's say we displace the object at x from its equilibrium position x equal to 0. Okay. So in order to displace it, we need external force which acts against the restoring force. Okay. And the work done by the external force is stored as potential energy. So in the case of spring mass system, the restoring force is Fx equal to minus of k into x, where k is the spring constant. So the external force will be external, that is equal to minus of the restoring force. So the potential energy will be U equal to integration over external force dot dx. Okay. As we displace from x equal to 0 to x, so the limit will be 0 to x. Okay. So this is equal to 0 to x integration over kx dx. Okay. So if we integrate it, we will have half of k into x square. Okay. And we can express it in terms of the frequency of the oscillation as the omega equal to square root of k by mass of the object. So it will be half of m omega square x square. Okay. Now if x equal to a into cosine of omega t, then we can express it in terms of the time. So that will be half m omega square a square into cosine square omega t. Now let's discuss about kinetic energy. Okay. So as you know, the kinetic energy Ek equal to half mass times velocity square. Okay. So if xt equal to a into cosine of omega t, so v will be dx dt. Okay. So this is equal to minus a omega into sine of omega t. Okay. So the kinetic energy will be half m into v square, that means a square omega square into sine square omega t. Okay. Now if we express the sine function in terms of the cosine function, then we can express it in terms of the displacement x. Okay. So let's write in terms of cosine square omega t. So that will be square into 1 minus cosine square omega t. So this can be expressed in terms of x. Okay. So that will be half m omega square into a square minus a square cos square omega t, that is x square. Okay. So the total energy will be E total. This is equal to kinetic energy plus potential energy U. Okay. This is equal to half m omega square into plus half m omega square x square. So this is equal to, so for a given spring mass system, mass of the object is constant and the frequency omega is constant and the amplitude a is constant. So the total energy is constant. Now let's draw the diagram for the energy for SHM. Okay. As the expression of potential energy is half m omega square x square and the kinetic energy is half m omega square into a square minus x square. So these are the equation of parabola. So if we draw the displacement versus the energy, so this green line shows the potential energy. Okay. and this blue line shows the kinetic energy. As the total energy is constant, that means it doesn't change with the displacement, so this line represents the total energy. Okay, so this point is half m omega square a square. Okay, we may also express the potential energy in terms of time. We already discussed about it as u equal to, okay, and that can be expressed as 1/4 m omega square a square into cosine of twice omega t plus 1. Okay, as the cosine twice theta equal to twice cosine square theta minus 1. Okay, similarly, if we write kinetic energy in terms of time, so ek will be half m omega square a square into 1 minus cosine square omega t. Okay, similarly, the kinetic energy can be expressed as ek equal to half m omega square a square into sine square omega t. Okay, and this can be written as 1/4 into m omega square a square into 1 minus cosine of twice omega t. Okay, because sine square omega t can be expressed in terms of cosine twice omega t by following this relation. The cosine twice theta equal to 1 minus twice sine square theta. Okay, so we can see that the potential energy and the kinetic energy oscillates with twice of the frequency omega. Okay, so if we plot it, this line represents the potential energy and this blue line represents the kinetic energy and this green line represents the total energy. Okay, and they oscillates with the twice frequency of the SHM. Now let's take an example. If the length of the string of a simple pendulum is L and its amplitude is theta naught, then find the maximum velocity of the bob. Now let's draw a diagram for it. The length of the string is L and the amplitude is theta naught. Okay, so when the bob is displaced at theta naught from its equilibrium position, it gains potential energy, that is the gravitational potential energy. If this height is h, then the gravitational potential energy is u equal to mgh. That is the maximum potential energy, right? Now h can be expressed in terms of the length of the string and the amplitude theta naught as h equal to length of the string L minus L of cosine of theta naught. Okay, because this thing is L cosine theta naught, right? So h will be the L minus L cosine theta naught. So the maximum potential energy is mgl into 1 minus cosine of theta naught. Okay, now when the bob comes at equilibrium position, its velocity will be maximum. So in other words, its kinetic energy will be maximum. That means whole potential energy converted into kinetic energy at equilibrium. Ek max equal to half m v max square. This is equal to mgh, right? That means mg L into 1 minus cosine of theta naught, right? So we will have V max equal to square root of twice GL into 1 minus cosine of theta naught.